Okay, I think we'll get started. So today we're going to finish up our focus on the electric field in this mini course on thermodynamics of fluids in external fields. After this lecture, we'll go on to do magnetic fields, and that'll wrap up the series. So today we're going to focus on electrostriction pressure. So we've been talking about the effects of the electric field on the volume of the material. And so let's just remind ourselves of the background apparatus that we're using for these thought experiments, and that's that Frank Apparatus. So I went through that in the first lecture of the series. But just as a reminder, we've got this piston that's taking up part of the parallel plates, and it can change its volume, and it has exposed to, or with pressure dealing with this piston, but it's also got a membrane here that's connected to a reservoir of that same fluid outside of the cell. And in general, these two, or so most often, these two will be the same. But we'll look at today a situation where we close off, or we'll look at the difference between these two. So we hadn't focused on this pressure to this external reservoir until today. All right, so first thing, let's get started with the Helmholtz version of free energy. And we have, we'll use the A prime so that we have flipped out the electric field with the polarization term. And now let's develop a Maxwell relation for this. And we're going to be looking at the pressure change with the field. We had been focusing on volume, but let's look at the pressure change. So we get a Maxwell relation here with these two. Signs are the same, so those will cancel. And so then we'll get dP dE over dVp dV. Now we're at the other variables that are held constant here are T, E, and N. So this is acting as a closed system. Now N is held constant. Now we can do this derivative here now. So we're going to have first times the derivative of the second. So I guess I have these out of order here. First times derivative of the second. So that'll be V depolarization dV. And then second times derivative of the first, which is just dV dV. So that's what we've got going on here. Now we are going to just put in what polarization is. And if this is the first lecture you've looked at and you haven't been going through the whole series, we are working in units where the permittivity of free space is set equal to 1. So there would be a permittivity of free space sitting out there, but just so that we don't have to carry it through all of our writing here. And then here we have E is constant, so that can come out, and then it's just d chi dV. So EV d chi dV, and this is actually chi electronic. Forgot the L there. Now, we can work with the electric susceptibility. Often in thermodynamics, one works with the dielectric constant, and so we'll use that chi electronic is dielectric constant over 4 pi. These are the electrostatic units we're working in. So we get a 4 pi out front, and then we get this factor here for this bit. And then, mistake here. We'll take the derivative of this with respect to V. Well, this part is just going to drop out, so we're going to have d dielectric constant, d volume here. So what is this? Well, that is the rate of change of pressure with the electric field under isochoric, isothermal, and a closed system here. And what does it say? It says this is how much this pressure P would have to change in order to hold the volume the same. So we turn on the field, there's going to be some electrostriction. If we reduce the pressure, then the volume will expand. And so this pressure, what this is telling us is how much pressure per field we have to release in order to keep that volume the same, to counterbalance that electrostriction. Okay, let's grab another Maxwell relation here. This is for the chemical potential, so we'll take this guy versus this one. So it's going to be the full chemical potential with the electric field, and then there is a minus sign here, so we're going to have d Vp dN, and then E. Now, there's a what we're going to do here is this. Notice this, we're under constant volume conditions here. So I could just pull that volume out, but what I'm going to write this as is as 1 over. I'm going to write this as I'm going to write this such that we have N over V here, and we're going to call this the number density rho. So this is the number density. And then I can write this expression as minus dE d rho. So we've done a, well, basically I've stuck in this here. And so the E comes out because we're at constant E. And so we're just the change in the susceptibility with the change in density. Now, let's connect this, what we've done here, and this pressure P out here. So let's open up this reservoir, and let's go under isothermal isochoric conditions, which we've done here, but in equilibrium now with the reservoir. So we're going to allow the reservoir to, we're going to allow the particles to exchange between inside the electric field and outside the electric field. The condition for that entropy, or that equilibrium, is that the full chemical potential with the field effect term in it for the inside bit has to be equal to the chemical potential to equal to the chemical potential of the reservoir bit. So d mu d mu r are equal. All right, well, inside, the full chemical potential is a function of temperature, volume, and the electric field. Outside, the chemical potential of the fluid in the reservoir is a function of temperature and pressure. So let's get our sense here. We've frozen this in place. So we've plugged this, we put a pin in here, so we can't change this volume. We're isochoric. And we're going to just let this be free. So the conditions that the reservoir experiences then is a constant external, or is a function of this external pressure. And so we can write this as T and pi here, capital pi. Now, this is just the math, so we'll write out the differential one forms, and so we just get each of the partial derivatives times their respective differentials. So here's for the full chemical potential inside the field, here's for the chemical potential outside the field. Now, let's consider this guy, and we can write the Gibbs-Duhem equation for that, which is simply minus molar entropy plus times dt, molar volume times d pi. So under isothermal conditions, dt equals 0. Equals 0. So this term will go away. And then we have d mu equals VDM dP. We can bring this over. We can, instead of writing isothermal conditions, we just write it as a partial derivative with temperature held constant indicated down here. So we now have, by comparison, this guy and this guy. And so this derivative here is simply equal to the molar volume. For the, and actually I should be a little careful here. This is for, I'm going to put a reservoir here. We'll carry this through all the way. So now we'll take the equilibrium condition, set these equal to each other, and so this should be reservoir. This is the molar volume within the reservoir. Now let's go ahead and integrate both sides. So we'll bring this over. We'll bring this molar volume over. Integrate the d pi, so we get pi minus pi naught. So this is when the field is off. Although the reservoir is not experiencing a field, but this is the field. So field off compared to pi when the field is on. And then we integrate up the dE, so we get a e squared, and then over 2. Everything else stays the same. This should be molar volume in the reservoir, and this should be in the reservoir here. And so now we have it in terms of the electric susceptibility. We can write it instead in terms of the dielectric constant, which is often what we would want to do in thermodynamics. All right, so this is coming from here. That's where that came from. And this is coming from here. So we've got a relationship now, but we want to compare back to this relationship that we've got over here. So this is the pressure change. This is if we allowed the pressure to change here under isothermal isochoric conditions. Well, the pressure does change under isothermal isochoric conditions. So let's look at this. Now we'll take this derivative, and I want to express it in terms of the volume up there. So by chain rule, this is d epsilon dv, dv d rho, and so this is going to be n molar volume squared d epsilon d rho. And so then we can cancel, this would be a reservoir, we can cancel one of the molar volumes. So I'm going to set this here. We'll cancel one of the molar volumes. We're going to have a n times a molar volume, so that's going to be V. And then this is now pi minus pi naught. So this is this one. This is this value here expressed in terms of the volume, so that we can do a direct comparison to what we got up here. So let's go ahead now and take this, and we'll integrate this up. We're going to get P minus P naught is E squared, and then we're going to have dielectric constant minus 1 plus V d epsilon dV. So this we've gotten by just taking the chain rule here, and then this we've gotten by going back to this and integrating that up. Now, what is this? This is the pressure on the tube when there's no field. This is the pressure when there's no field. So those are equal. So these two are equal. And so now let's subtract the pressure outside the field, the pressure on the reservoir, from the pressure on the fluid within the field. So we get P minus pi, and it cleans up very nicely. So this is for isochoric, isothermal conditions. And this represents then the difference in pressure between these because we're trying to hold the volume constant. So notice it is it's missing this term here. So this term, if we're not allowing this reservoir to be involved, so if we're under a closed system situation, then we have this change in pressure due to the field's action, but we also have this response of the material, and it's nothing this can do about it. So this is what wants to suck in more material, but it can't. So we talked about having to relieve that pressure in order for that volume to expand. Here, now we're looking at opening this system so that we can let fluid in if it needs to, and it exactly accounts for this. And so the pressure difference is just that difference due to the development of the field in the material. Okay. Now, let's grab something from a previous lecture. So we worked this up, I think in the last lecture or the one before that. The isotonic condition here. And we got this. So let's go ahead and integrate this up. We integrate this up and we get the exact same formula. So the isothermal isochoric conditions now with a reservoir is going to be equal to the pressure difference here, just the simple pressure difference when we're allowing the fluid to flow. And so that makes some sense. What does this mean? This is the pressure difference between here in order to keep that volume constant. What does this mean? Well, this just means the material is always going to be in equilibrium. So this is a little self-consistent check here. This original P, the difference here now, this is the external pressure of the reservoir, and then this would be just the original pressure here compared to the final pressure. All right, so that kind of covers it for the electric field. We want to talk a little bit, just as a quick example, of a very simple model for determining the partial molar volume for ions in water. Now, this is going to deviate from what we've talked about. So we've been talking about this Frank apparatus, which is a nice uniform field for us. So we're not going to get into the Coulomb field associated with an ion, but just as a quick example to show why electrostriction is important, let's look at the molar volume when we dump ions into water. So there's going to be an electrostrictive term that is going to cause an internal pressure to change when an ion is introduced into the water, so the local environment around the ion. And that is related to this electrostrictive term that we've been calculating. Now, I'm using the same symbol that we've used in this sequence, but this is not for the Frank apparatus. So the formula that we got before is irrelevant to this. But there is some notion that a good approximation for the electrostriction around the ion is something that drops off as r to the fourth power. So we can integrate this up, this delta V, and this would be the change in volume due to this electrostrictive piece. So we integrate in spherical polar coordinates, so we get this, we've integrated out the angles, so we have the 4 pi r squared dr, and then we integrate this, and we get something that is going to be proportional to, and I should say this is proportional here. It's proportional to, so we're going to use as our constant of proportionality here, we'll call that lambda 2. So that's just our constant of proportionality. Now this is just the electrostrictive piece. So now let's think about the molar volume for putting an ion into solution. So we put the ion into solution and it forms a cavity. And so we would expect that the volume contribution to that ion should be proportional to the volume of that cavity. And so indeed, we are going to have a lambda 1 here, constant of proportionality, for a r cubed term. So that's this volume of this sphere. And what r is here, r is the ionic radius. Now, it's not obvious what radius to use. So we can get crystallographic radii, so the ions in the crystal. But when that comes out of the crystal, the radius of the ion differs. Furthermore, when it's in the solution, the response of the solvating molecules are different than the molecules in the lattice of the solid. So we can't anticipate that we should just be the volume of a sphere of the size of the ionic radius. And in fact, that's not it isn't the case. In fact, experimentally, and we'll get some examples here, that it's about twice as big as that. And so the volume that it takes up just being in solution is given by this term. This is number of moles times Avogadro's number, so this will be on a molar basis, so this would be partial molar volume. And then the electrostriction comes in negative because it's compressing the fluid, so that's going to contribute to lowering the effective volume of these, or partial molar volume of these ions. Now, it turns out that cations and anions affect the solution differently, and the experimental results, anyway, say that most cations are such that the constant of proportionality for the spherical area term is about 5.3, and the constant of proportionality for the electrostrictive term is about 4.7. Anions have a larger effect on the electrostrictive in a relative sense. So anions have 4.6 as the effective volume, spherical volume, and then 19 for the constant of proportionality for the electrostrictive piece. So quite a bit more effective, at least in this model, comparing to experiments. All right, so this is electrostrict pressure, and we finish up now the effects of an electric field on our fluid. So next we'll move on to magnetic field. We'll just have a couple of lectures there, because a lot of the stuff will be pretty similar to what we've done here. We can talk about it in magnetostriction, but we're going to also talk about adiabatic demagnetization, which is a method for getting very, very cold temperatures.